everybody. Welcome to Monday morning's edition of Algebra 2 notes. That's right. You guys are here to get the notes for our next lesson, which is on average rate of change. Average rate of change. We are on pages 81 and 82. Okay, I'm here to go over these notes to teach you as best as I can through this Chromebook. So please do your best to soak it all in. Take your time, really think about what I'm going over here. Do your best to understand so we can figure it out. What is average rate of change all about? That's what we're going to figure out today. This should be a familiar term to you. Hopefully this is not the first time you're hearing those words, average rate of change. I very much hope not. But if so, that's okay. We'll make the best of it either way. We'll do what we can to learn it and to understand it and to be able to apply it. Okay? So when we model using functions, we are very often interested in the rate at which the output is changing compared to the change in the input. So how fast is the output changing with respect to the input? If we're talking average rate of change, a rate deals with two different variables. Okay, like your speed when you're driving in a car is miles per hour. That is a rate, something per something else. Okay, so just kind of keep that idea in your minds here. So here we have the function f of x. Just going to label that. It's graphed right here, f of x. Evaluate each of the following based on the graph. So f of 0 means what is the function value when x is 0? So when x is 0, f of x equals 1. So f of 0 equals 1. When x is 0, y is 1, right at that point there. What about f of 4? Well, when x is 4, looks like the function is 7. F of 4 equals 7. Okay, f of 7. What's that function value when x is 7? Well, the function is 10. It's equal to 10. And f of 13, this last one over here, when x is 13, the function or y value is 15. Okay? It was nice that each of the points we were asked to evaluate were very distinct on our graph here. First one, second one, third one, fourth one. Okay? So those are our function values for each of those. Letter B says find the change in the function. So the change in f, delta f, that little triangle is a math symbol for change. Okay, the change in the function over each of the following domain intervals. You find this by subtraction and show the change on the graph. So we want to find the change in the function over the interval 0 to 4. Okay, from 0 to 4, how much did the function change? Well, it ended here. That was where the function ended at when x was 4, but it started all the way down here. So what's that difference there, that subtraction? Well, up here the function was equal to 7. Down here the function is equal to 1. So that change in the function equals 7 minus 1, which equals 6. And again, that's shown from here down to here. And then we're looking at the interval from 4 to 7. From 4 to 7. So where did our function end? It ended up here, and it started right there. So at the end of that interval, our function was equal to 10. And at the beginning of the interval, our function was equal to 7. So the change in the function then is 10 minus 7, which is equal to 3. All right, and our last interval from x equals 7 to x equals 13. Always ended there, started there. So subtract those values. That end value was 15. My change in f is 15 minus where that function started at 10, which equals 5. So the change in the function that first interval was 6. Second interval, it was 3. Third interval, it was 5. So the question then, why can't we compare these three changes, the changes in the function, to determine over which interval the function is changing the fastest? Okay, why can't we just use those values? Well, think about what I said before. If we're talking about something changing, how fast something is changing, you have to compare that change to something else. And right here, that's only taking into account the vertical change. But you can, if you want to think of it like this, it doesn't take into account over what time that vertical change is happening. Because think about this, again, speed in a car. If you say you drove 50 miles, one day you drove 50 miles, another day you drove 200 miles, right? 50 miles and 200 are clearly different miles. But because you drove 200 miles and that's more than the 50, does that mean you were driving faster when you drove those 200 miles? Or did you just have more time to drive that distance? So, right, one value like this, the change in the function, does not give the whole story. These changes don't take into account the fact that they're happening over different x intervals. So we have to take that into account. Okay, it's not just about how much the function has increased, but over how big of an interval did that function increase. Okay, so we can't simply compare those changes. These changes don't consider the domain interval. Or I should say the different domain intervals. All right, because really we're just comparing those vertical changes. But when we're talking about speed and changing the fastest, we need to compare that to the other variable. All right, so now we get to actually calculating the average rate of change for the function over each of the intervals and determine which interval has the greatest rate. So to find the average rate of change, like I mentioned, if we're talking miles per hour, right, we have one variable divided by the other. The number of miles you go divided by how many hours you were driving. So we use the change in f, the change in the function, over the change in x. Change in the function over the change in x. So from 0 to 4, our domain interval here, our function changed by 6. So that change in the function was 6 over the change in my domain, which was 4 minus 0. So I have 6 over 4, which equals 3 over 2. That was the rate of change, the average rate of change over the interval from 0 to 4. Okay, what about from 4 to 7? Well, again, you want to take the change in the function over the change in x. So that equals the change in the function I already figured out up here was 3 over the change in x. I go from 4 to 7. So that gives me 3 over 3, which is equal to 1. So the average rate of change on that interval from 4 to 7 is 1. Because we took the change in the function, compared that to the change in the x's. Change in y over change in x. Last one here, same thing again. Okay, the change in our function from 7 to 13 was 5. Over my change in x, which is 13 minus 7, gives me 5 over 6. Okay, so again, the rate of change, the average rate of change on that interval from 7 to 13 is 5/6. So now it says, using a straight edge, draw on the lines whose slope you found in part D by connecting the points shown on the graph. So I don't have a straight edge here. It's a little hard to use on this board, but please use your straight edge. There's one slope there. There's my second, and there's my third. All right? So each of this 3 over 2, that average rate of change, 3 over 2, is represented by this line here. This 3 over 3, or this average rate of change of 1, is represented by this line here, that middle line. And this last rate of change, 5 over 6, is represented by this line here. That is the slope for that line. So based on these, which one has the greatest rate of change? Well, 1 is greater than 5/6, but 3/2, 3 over 2, is greater than 1. So that means in this first section here, in this interval, this is where the function had the greatest rate of change. It was increasing the fastest right here. Okay, so just to wrap that up, the average rate of change, again, it mentioned that that's the slope of the line. So the average rate of change, the average ROC, or slope, measures the steepness of the line connecting the 2 points. Okay, the average rate of change or the slope, those terms are technically interchangeable. The average rate of change or slope measures the steepness of the line. The steeper the line, the greater the rate of change. The faster that function is changing. Okay, the steeper the slope, the steeper the line, means that that function is changing faster in that interval. So the function, again, is changing the fastest in this first interval because it has the greatest rate of change. It's the steepest section. Right? On to the back. Again, it just reiterates that the average rate of change is an exceptionally important concept in mathematics because it gives us a way to quantify how fast a function changes on average over a certain domain interval. And in higher math, there's a lot of focus on comparing functions. Which one's changing faster? Why is it changing faster there? Okay, there's a lot of stuff that can be done with the average rate of change. So we already used the formula, but we have it formally written down here. For a function over the domain interval from A to B, the function's average rate of change is calculated by this. Okay, the change in f over the change in x. You can also think of that as change in y over the change in x. Okay, the change in y over the change in x. or the change in the function over the change in x. Or like they say here, the change in the output over the change in the input. Those things are all the same. They mean the same thing. All right, then they write it here too as f of b minus f of a over b minus a. So they're taking the inputs to get those outputs, finding the difference, the change in the outputs over the change in the inputs. And we're going to use this piece of the formula in this exercise here. So consider the two functions, f of x equals 5x plus 7 and g of x equals 2x squared plus 1. Calculate the average rate of change for both functions over the following intervals. Do your work carefully, as always. Be careful when doing your work and show the calculations that lead to your answers. So my x interval, my domain interval, goes from -2 to 3. So from -2 to 3. So I don't know the function values yet for those inputs, for those x values. So I need to use those x values, those inputs, to get my outputs. Otherwise, I will not be able to determine the change in the output or the function change. So I'm going to take